output that you, binary output that you distribute. Runtime, where the multi-stage operations happen when the software is run on a user's machine. Mixed time, which is where some of it happens at both. And then our categorizations weren't as good as we thought. So, it turns out once you start getting into multi-stage programming, the distinction between compile time and runtime gets a little bit blurry and starts to be meaningless in some applications. So it's worth keeping an eye on those our categorizations weren't as good as we thought things. So, some places you can use multi-stage programming include optimization. There are some optimizations that your compiler won't know how to do because it's only useful in this specific case. And when you need the speed up, like for a linear algebra library or a database query interpreter, it is very useful to be able to use multi-stage programming to implement that optimization portably and easily and reusably. Time saving. Multi-stage programming can save you time writing code. It increases the amount of things you can abstract and the types of abstractions you can make, and it lets you do a lot of things that would be very difficult to write normally without much code. Resource inclusion. Sometimes you'll want to package something into the binary, and rather than needing to write an entire extra tool to embed something into your binary, it's just a one-liner to open up the file and then splice it in as a literal. Pre-computation. If you have an expensive operation that produces constants, like say the lookup table for a sinusoid, pre-computing that is nice. And with multi-stage programming, you can do that pre-computation at compile time easily, and then have it just be static constants at runtime. And DSLs, the point of the class. Multi-stage programming is wonderful for implementing domain-specific languages. Once you learn how to do multi-stage programming, it'll take you 1/10 as long to make a DSL, and you'll get 20% more improved speed at least. So, language support. There are varying amounts of language support for multi-stage programming. So, good language support, you've got things like OCaml and meta-OCaml. Common Lisp and Scheme have really nice macro systems that allow you to do multi-stage programming. And then Terra and Zig are also good at this. These are both languages that provide semantics and performance similar to C, whereas these are much more high-level languages. We'll be using Terra for reasons I'll get into later. Other languages also have somewhat less support. Groovy has Groovy's operator overloading and and syntax and method parenthesis omission capabilities make it possible to do some pretty convenient DSL and a little bit of multi-stage programming in Groovy, but the performance cost of doing that is quite large. Kotlin, similar to Groovy, it has some nice support, but isn't terribly optimized. Haskell. Haskell's type classes allow you to do quite a bit of multi-stage programming, but then you run into some very sharp limits where you can't use more than one of them at once in interlocking manners. Forth, which I talked about at the beginning of this class, has pretty good support for multi-stage programming. You can define words that define other words, that compile things into word definitions, whatever. However, because it doesn't have the same high-level operations and convenient representations for manipulating code trees as the other languages, I can't say that it has great support for multi-stage programming. And C# has a surprising amount of multi-stage programming support. Besides being able to write and load your own MSIL bytecode at runtime, it also has expression tree classes, the ability to introspect on the ASTs of code, the ability to dynamically generate, type check, and compile ASTs at runtime. Although I do have a whole rant about problems in this section from writing 1,000 lines of code against it while I was working at Microsoft, then C++, C, Java, and Python. C++ templates, C macros, Java annotations let you do a little bit of it. Python decorators also can do some of this. but of course the performance of these is bad, they are not very expressive, so I'd recommend trying to stay away from doing too much multi-stage in those languages, although it is possible. So, C macros. I assume everyone here is familiar with C macros, but they just do basic textual substitution with a tiny bit of fanciness for detecting where tokens begin and end with white space and handling the operators properly. So, and I will be very particular that these are not proper macros. Calling them macros is an insult to the term macro. Or you can use a separate preprocessor. Something like Seaside, which is something from the GNU project that allows you to write a logic table or a lookup table in the comments, and then it will expand it into a ton of branches, checking all of the conditions to figure out optimally which set of actions to perform for it. And Dynasm is a preprocessor for C that allows you to write inline assembly instructions into your C, and then it will generate the compiled form of those assembly instructions into a buffer at runtime, which allows you to conveniently write little assembly templates for functions, and then templatize and instance them at runtime, and then call them immediately. This is useful for writing just-in-time compilers in C. It's used in the LuaJIT project. You can also use it to do optimizations like a branchless binary search. You can use Dynasm to generate the assembly code for a very simple binary search using x86 conditional execution instructions so that it can perform an entire binary search given a fixed length thing without branching, which makes good use of iCache and doesn't break your branch predictor at all. So, because doing that requires knowing ahead of time the fixed length of the thing you're searching over, by using Dynasm, you can generate specialized ones for whatever length of list you're searching at runtime. So, are C macros Turing complete? I'm guessing that's a question you've never had to think about before today. Anyone want to shout out an answer?
Yes.
No, but they are close.
Okay.
So,
No, he just said yes, that he wanted to shout out an answer.
oh, okay. So, they are not Turing complete, but you can get close. And it's a really bad idea to do things that make you question, are C macros Turing complete? So, some limitations in C macros: no more than 63 nested parentheses. You can't have more than 63 characters distinguishing a name. You can't have more than 4,095 macros defined at once. And you can't have more than 4,095 characters in a single source line. So you can do some shenanigans with church encoding to do math with macros in C.
Oh.
Like expanding a macro to f of f of f of f of x, and then defining a macro that replaces f with something else, and then turning those into 1 plus whatever, and then it constant folds back to a single constant. Don't play around with that. You will regret yourself. Cthulhu will eat you. So, polymorphic functions in C. We can use C macros to do the most common use case of C++ templates. You can have a macro that accepts the name of a type and then expands to a function. It can create the function name by concatenating the name of the type with the function name so that you can have add underscore int, add underscore float, etc., and have that work for all of the types. You can write some additional macros to make it easy to write that function so that you can just write the function like you would normally write a function, and with a couple macro invocations to transform that definition into a macro that expands your template. And then you'll also want a macro to figure out what the name of a templated function is so that you can use templated functions in other templated functions without redefining them every time. Yeah?
I actually saw the other day something about using decal type to get the
Decal type is a C++ operation, not in C.
So this is just in straight
This is
C.
C99.
Got it, okay.
So, C++ templates. another layer above C macros. These things are Turing complete, which of course by the halting problem and the way C++ syntax is defined, means that it is now undecidable whether or not a C++ program is syntactically correct. You can write a macro, you can embed the halting problem into your macro definitions to make them either evaluate to a type or a value, and syntactically you're not allowed to use those interchangeably. So if a value is in a type place, it's syntactically incorrect, which means it's undecidable. And these are cumbersome and slow. Andrew, I believe you have a story about trying to write unit conversions with C++ macros and how annoying it was. And anyone who's used Boost knows that C++ template expansion is slow. So it's not very expressive. It is not a good tool for doing effective multi-stage programming. So let's talk about hygiene. Multi-stage programming working effectively depends on having good hygiene. C macros do not. When you define a name inside a macro, it's in the scope of the place that's calling the macro, and names used inside the macro are also in the scope of outside the macro, which means that if you have a name conflict, everything breaks. You can't use a namespace inside a macro without polluting anything outside the macro, which causes everything to break. It produces really hard to debug errors. So these are two things that will be fixed by correct and useful implementations of multi-stage programming. Also, operator precedence. When you're using a string substitution-based macro processor like C, it screws up your operator precedence. That's why you see so many extra parentheses everywhere in C macros. Because if you don't, depending on where you expand the macro, some operator might bind to part of your macro expansion, and then your operator precedence will be wrong and everything will break and it will be impossible to figure out where it came from. All right, so doing it right. Well-defined operations. Things that don't have weird, unpredictable effects, that do good abstractions. Operations that do exactly what they're supposed to do. Magic A is magic A. And code is data. Remember this from von Neumann computers and the basis of all of the computers. Code is data, so it should be conveniently manipulatable as data when you're doing your multi-stage operations. Convenient representations. A string is a terrible representation for doing manipulations and transformations on source code. Trees are much better. And paradigmatic properties. For those of you who've already seen my multi-stage paradigm talk, I mean some very specific things by that, but we don't have time for me to go into detail right now, so I'm just going to gesture at that vaguely. So, language choice. The rest of this presentation is going to be using Terra as the language of choice, because it has C-like low-level semantics, so it should be familiar to you guys when we're working with it. It has high-level semantics that act like a dynamic language, which is a whole lot more convenient for throwing code together than if you have to nursemaid pointers around through everything transforming your trees. Simple and learnable syntax. It has a really quick and easy syntax. It should just make sense to you right off the bat, and the amount of syntax you'll need to learn to use it is small and fits on a fairly short web page. And it is fast and efficient. Both the high-level dynamic stuff and the low-level stuff are very fast, very efficient, and nice and easy to use. So, there are other languages, but I think Terra is the best choice for doing this right now. So, some resources for Terra. These are links. Oh yeah, I probably should have told you where the URL for where this presentation is. It's marker word. Multistage. So aiverson.me/presentations/multistage.html, that has a current live instance of this presentation with clickable links and download links as well. So,
All lowercase?
yes. The fundamental operations of multistage programming. These are the operations you need to do it. Quote, which is sometimes called quasi-quote for distinctiveness, a splice, an escape, an emit, and a way to generate symbols. So, first let's talk about quotes. A quote is an expression that evaluates to an AST of the quoted source code. And this is sometimes called quasi-quote to distinguish it from the string quote. A string is an expression that gives the contents of the quoted source code as a string. A quasi-quote is an expression that gives it as an abstract syntax tree. And this is what it looks like in Terra. There are a couple forms: quote, list of statements, and then optionally in expression, which lets you define variables, do some operations, and then have the whole thing evaluate to a single expression, or a single backtick followed by an expression, which just is a convenient way to get a quote of an expression. You've got your block syntax and your expression syntax to let you conveniently get either. Yes?
So that bottom line where it's quote A times B plus C, that's the whole expression A times B plus C as the AST,
Yes.
right? Not just A?
Correct. Yeah?
So, in the first one, you've got the in, right?
Yes.
How do the two pieces of the block get differentiated in shorthand form?
This is empty in shorthand form.
Okay.
So, and you can also leave this part out as well.
Okay.
That just gives you a quote of a series of statements rather than an expression that has some statement dependencies. So if you need a really complicated expression in your quote, it's frequently easier to just define it by binding variables and then building an expression out of those variables. Or if you have something statement-like that needs to fetch some resources and then evaluate to it, like say an expression that evaluates to the parsed thing coming out of some file, you can do that as well. Splice. Once you also need a way to put quotes back into, or to put the AST from a quote back into another part of the AST, so that you can move code around and deal with and generate it. So you can enclose an expression that happens to evaluate to an AST, and then compile the resulting AST into the code that the splice is in. So say we have an expensive operation on a compile time constant that we don't want to compute in this quick inner loop every single time through. And so because in Terra, every constant or a number literal or a single number is a valid AST for a number literal, any function that evaluates to a number, you can just splice in as a compile time constant. So this expensive operation happens once at compile time, and its result gets compiled into the code as a constant. Yeah?
Are the brackets the splice operator in this
Yes,
case?
the brackets are the splice operator. Next, escapes and emits. We've gotten a way to do expressions, but sometimes we'll also want to do it with blocks. It's entirely possible to do everything with escape and emit using the normal splice operator and an immediately invoked function expression, but escape and emit lets you do it more cleanly, and it makes it more obvious what's happening. And obvious and cleanliness are very good properties of code. So for an escape, we just use the keyword escape, which starts a block. So we've got Terra and Lua contexts. Inside a Lua context, quote starts a Terra context. Inside a Terra context, escape starts a Lua context. It just evaluates this block, and then there's a little function emit that will build up ASTs in place of the escape. So let's say we're compiling a simple little fake assembly language. We can write a little line, or a single line of Terra in a quote for any given operator in the assembly language. And then to compile it, we just make a function that has the AST from that little, or the quote from that little line of Terra code corresponding to each instruction. We just loop through every line in our fake assembly, look up the Terra quote for each line, and then emit them into our function. And then this is a very quick and easy way to compile your fake assembly language syntax into native code. Does that make sense? Yeah?
Where did the fake ASM variable?
Somewhere outside here.
Okay.
So like this is inside a function compile assembly. And then this fake asm is a variable that gets passed into that function, and then the compile asm function returns this compiled function. Yeah?
So am I right in thinking that, so Terra is our main language and then Lua is our meta programming language? Like
Yes.
Lua is like the templates of this language?
Yes. Or
Or
Terra is embedded in Lua. So you start in Lua by default, and then you introduce a Terra context
okay.
and build some Terra objects, and then back in Lua you say, here, save me an executable of this.
Gotcha. But the emit code will end up being Terra code, right?
The thing that gets emitted
Yep.
is an AST of Terra,
Cool.
but this block here is in Lua. So, generate a symbol. This, yeah, in addition to the other things before, sometimes you need to make something go a little bit non-local, or that to break a lexical scope, or just create a new variable name to store a temporary that doesn't conflict with anything so you can access it later. There are 3 ways to do this in Terra. In Lisp, it's just a single gensim. Did you think I'd get through the presentation without talking about Lisp? But in Terra, you've got 3 different ways for 3 different contexts you can use a symbol in. You've got a local variable context, which, because Terra is statically typed, you need to declare the type of the variable, and then optionally you can give it a name which is useful for debugging. You can make a global, which has at least one of type and initializer value, and then optionally a name. So you can either create an uninitialized global with a particular type, a global with whatever type fits the initializer, or a global with a specific type and a given initialization value. Then you can also label a name, or make a label with a given name. The name is optional here. A label is just a thing you can go to. And Terra does support goto. You're discouraged to write it by hand, but it's allowed because it's really useful for generating certain types of code. It's not, you shouldn't write gotos by hand, but generating them procedurally is useful, so it's allowed. We good here? Okay. Type manipulation. Manipulating types for metaprogramming static languages is really important. So we need to be able to dynamically create and manipulate and use types. We need to be able to instantiate types from a template given something. We want to be able to read in a JSON schema or an XML schema and produce a memory mapped structure corresponding to the variables and types in that schema for use in our code later. We want to be able to use an SQL database table description to create a type that stores that as raw memory and pointers. Template specialization and meta behaviors. Things like being able to interact with some other object system or some other library conveniently, yeah?
So would like .NET's entity framework be a form of like converting some schema to data objects in this sense, or is that a little bit too high level?
Yes, that would be an example of it, except that, well, okay, I actually worked on the source code for that.
Ah.
So it is an enormous project, multi-tens of thousands of lines of code to generate these type declarations in various forms. In Terra, you can do it in under 100 lines.
Got it. So it's
So
the goal
yes, that is an
small.
example, but because C# is really bad at this, don't compare what you can do with the entity component framework to doing what you can do with Terra and proper metaprogramming.
Got it, okay.
Okay. And types with meta behaviors. Things like dynamically generating methods as they're needed to be able, is really nice to be able to conveniently implement a variety of patterns. So, metaprogrammed types. We can create new methods when needed, not when nested, darn it. I'll fix that. We can store meta information on a type. Because Terra types are just Lua tables, you can arbitrarily add any data with any key you want into them. So you can store pieces of Terra quotes that you can use to build up complex access behavior later. You can store, debug information about where and how it got generated. You can do whatever you want to them to build whatever is useful to you at the time. And you can transform a type to add members and methods, yes?
So along those lines, could I create maybe like an integer type that only accepts values between 0 and 100?
Absolutely. Cool. But you can, that's really easy to do. Like you, I should show you how the automatic differentiation engine that's built into the Quicksand probabilistic programming language. It uses similar approaches, and it's significantly faster than the implementation in C++ of the fastest automatic differentiator they were able to find, and uses less memory. So, and macro. A macro is an implicit quote and escape that just blends into normal syntax so that it works like it. So you can create a macro by calling the function macro on any function that accepts ASTs as arguments and returns an AST. And then you can just use it in Terra like a function. And this is syntactically equivalent to splicing in the result of calling the function that the macro is wrapped around with the ASTs of its arguments passed in as arguments. So just saves a little bit of typing, blends in easier. So nice and convenient, not too hard. Make sense? All right, before we get onto this, let's talk about where metaprogramming is used already. We've already talked about Microsoft's entity component frameworks, but there's also FFTW, the fastest Fourier transform in the West, or Fourier for the win. This uses metaprogramming operations to, not very well because it's C and uses separate executables for its pre-processing steps, so it's way longer than a corresponding implementation in Terra would be, and it's taken way more effort to build, but it's very fast. The fastest Fourier transform implementation that's open source and available right now. So that's an instance of using optimization, or of using metaprogramming for optimization. Additionally, the Atlas linear algebra library. Atlas uses metaprogramming. It uses C and C++ assembly intrinsics to get access to SSE instructions and vectorization operations, whereas in Terra you can just do that as first-class vector calls and such. It also uses a multi-thousand lines of Ruby to generate multi-thousand lines of C to generate the actual Atlas executables and shared object libraries to do the linear algebra operations. In Terra, for one of their papers, they wrote a 50-line implementation of a matrix multiply kernel that's 80% as fast as Atlas, and way faster than Atlas was before they fixed a bug in it that they found because they were writing this paper. So those are some examples of using it for optimality. TensorFlow also uses some of this stuff. I don't feel like going particularly in depth about that one. Seaside is, I've mentioned it before, is an example of saving yourself time with multi-stage programming. In Seaside, you write a specially formatted comment containing a logic table, conditions for what rows on the logic table happen, and then actions for which rows happen. and then just a grid of zeros and ones for which conditions need to be met for which actions to happen, and it transforms that into a really long block of nested if statements and else ifs and everything to optimally check those conditions with as few calls as possible, and then execute all of the operations requested. Yeah?
So in this example here, what's the kind of difference between just saying content array without the local equals contents? Right, because if it's not local, it's global in Lua, right?
Okay, this is creating a Terra global, not a Lua global.
I see.
So this is creating a global variable that can get compiled into your executable containing the content of the file. So it grabs the content of a file, which, say you're writing a command and it has a long list of things to print out when you call help. You can just have a text file containing what you want it to print out, and then just splice that text file as a constant array, or as a global array. And because metaprogramming, this doesn't actually need to be global, it's just called that. You can make it act like a static variable in C. Yeah?
So this might be a dumb question, but is Terra compiled or interpreted?
Yes. So you can use Terra in a lot of ways. You can use it as like a Lua interpreter, but with high performance extensions. You can use it as a mixed, or as a compiler to build other languages on top of, and you can use it as its own compiled language that outputs object files, dynamically linked libraries, and executables. You can even potentially write bare metal code in it.
Cool. So that last use case would be like where we would actually just have the constant in like the static section now, right?
Yes. So you have a file on your development machine that you need to have access in the executable, but you don't want to deploy an entire archive full of things to the computer, so you just compile the contents right into your executable.
I really like it.
Yeah.
I need to fix that.
Now, there are other ways to do this using, but they're really complicated to do in C because you kind of need extra executables and scripts. For instance, you might write a script. I've seen scripts like this in Lua that read in a file, convert every single call to string on every single byte in the file, and then concatenate and generate code out of it that says character array equals array literal number comma number comma number and so on for 1,000 lines. Which having that as a separate executable rather than being able to just splice the contents in is way less maintainable. It adds an extra build step, it makes your dependency management harder, and it's a bit more fragile. So this is an easier way to do it. It's cleaner, it's faster. Yeah?
So then, another thing that, I don't know if it directly corresponds, but with C# and .NET assemblies, you can add files to the manifest that will be compiled into the DLL
Yes,
assembly.
like that. But
So,
instead of needing specific support in your compiler and build chain and manifest tools, the entire stack up and down there, you can just do it yourself in a line.
got it, okay.
So, and that pattern holds. Things that would take modifying your entire compiler and IDE toolchain in other languages are 1 line, 10 line, 100 lines in Terra.
Okay,
Yeah.
thank you.
Yeah. So this is interfacing with Objective-C. Objective-C has a weird meta-object protocol that allows you to send messages with dynamic types and stuff like that. So has anyone here actually written code using the C API for Objective-C? How about for Java objects? Okay, well, writing those requires writing for every single call. You need to write a whole bunch of lines to look up metatable, or to look up method tables on objects, manually indirect through a vtable, check your types, pick out the correct overload of the method, and then serialize your types across and call it. Instead, we can write an __method missing meta method, which, when you try to call a named method on a handle for an Objective-C object, generates the code to do that for you. You write the code to generate that code once, it's short, and then you can just call Objective-C meta objects with all of the overloading and meta methods, just like you're calling a native Terra object, and it will just work. Which is amazing if you've ever actually tried to write against the C APIs for Java or Objective-C like I have. It is pain. So, going over how this works, we define a struct for Objective-C which has a handle that is a pointer. Terra uses ampersand and @ instead of star and ampersand for its pointer operations because that fits in better with the syntax and grammar of Lua as it's embedding in there than using the equivalent C operators would. So minor sticking point for conversion, but that's one of the harder things to notice, or so everything else is easier than that. Then C equals terralib.include C. Just include the C header. You can directly include any C library or header in Terra. For the Objective-C message stuff, create a pointer to an Objective-C object handle, and then put a meta method on it that when you call, or that is a macro for when you call it with a particular method name, the object that you're calling it on, and a list of parameters. It will figure out the proper selector, the proper dynamic vtable, the vtable address for that given method name, parameter numbers, and then it will create an expression that will call Objective-C message send to invoke that object with its Objective-C handle on that vtable entry with the appropriate arguments. Does that make sense?
It would make a lot more sense if I had gone through and had to write like the interface code beforehand, and then I notice the pattern, right, and then I make the meta method. You know, just staring at it, having never interacted with it, you know, not super clear, but I get the idea of it.
So this, instead of requiring you to write c.objective-c underscore message send of object.handle, comma, c.cell underscore register name of sanitized selector of cell, comma, 3, comma, ABC, close paren, you instead just need to write object::method ABC. Yeah?
So does this replace the method name in the Objective-C object methods? Because it looks like it would just call this every time you try to call a
Yeah.
given okay.
So the struct Objective-C doesn't have any methods defined on it right now, and it has a method missing meta method. So whenever you try to call a method, it sees if it's defined. Since there's no method that's defined on this, it never is. It asks method missing for what should I do instead if a method missing exists. In this case, it's create the code to index the vtable for Objective-C. Oh, and you'll notice this c.cell underscore register name, this happens during the expansion at compile time rather than at runtime, which means this is faster than doing your code by hand, or doing the code by hand. Because instead of needing to keep an enormous list of global variables of all of these and then add something new to it and remember all of the names whenever, or putting it at the runtime, which requires you to do a little bit of string manipulation every time you need to call a method, it compiles it in for you and makes it fast. Yeah?
I guess I've never used Lua method missing before, so does that replace...
This isn't a Lua thing, this is a Terra thing.
Okay, does it replace the function you tried to call with no longer missing then?
It does not.
Okay, so every time you call it, it does this?
Right. You can make it register a method on the struct Objective-C, but why bother?
I guess I don't see how this saves you anything then.
Because
You have
this
to-
happens at compile time.
Okay,
So even though you're recalling it every single time, since it all happened at the
You're-
compile time,
yeah.
it gets,
okay,
It translates your method call at compile time into the Objective-C syntax and pre-computes things to make it run faster.
okay.
So, object systems. Terra doesn't have a large object system built in like Java or Go. However, in the tests, they write a Java-like and a Go-like object system in Terra in like 200 lines of code that implements all of the features of both of those object systems just as a test to see if it was working properly. Terra lets you use any object system you please. They've got several pre-built ones you can choose from, or you can write your own with extra functionality if you need it, and it's not hard to do. So for things like that, you need to do things like create vtables, figure out dynamic bindings, and check instance types. Creating vtables is not terribly difficult. Because the things are just Lua, because the struct definitions are just Lua objects and Lua tables, you can just iterate through the list of methods in a particular, defined on a particular structure, and then build a table or an array that lets you map between the name of the method and the method itself at runtime. Then when you use that as a vtable, you can pass handles of that around so that when you have a child object or a inherited object of a parent object that overrides a method, when you try to call a method on the parent, you can dynamically bind it. Because the section of the vtable corresponding to the parent's method will always be a prefix of the vtable of the later, the vtable offsets you get from the parent interface will just give you the functions of the child when you pass that back. And then you've just got the ability, as long as you check your instances, which you can interface with a type system, so you can make it do the casting checks for you and do all of the casts correctly by implementing an __ cast meta method, which will give you all of the semantics of automatic type promotion, manual casting, inheritance, interfaces, etc. from Java, except it will run faster because you've got a better optimizer and you're compiling directly to native instead of JVM bytecode. And you can do the same thing for Go's type system as well. And this time I'm going to remember to plug my laptop in before it dies. So, let's talk about compiling VF. I expect that several of you have heard of this language before, where you've just got 8 character operations and it's barely Turing complete. Every character except for your loop operations are a single line of code in either C or Terra. But in Terra, you can quote and splice those things together and just generate a compiled function. There is an example, there is an implementation of this on the website, just on the front page of writing a compiler for BF. So I'd recommend taking a look at that at some point when you're working on the homework. You can then maintain a stack of labels that you push and pop off of as you see your matching square brackets for your conditionals and loops. And then you write a simple implementation of what each character in the language does. In Terra, you then concatenate all of those implementations together by splicing them in, just like in the fake ASM example I showed earlier. And then you've compiled a language, a minimalistic language to native code. And it'll take you less than 100 lines to write a compiler to native for this language. I'm not asking you to do that on the homework though. So, effectiveness. What makes multi-stage programming so effective? Well, it makes the language better. It allows you to extend the language to make your application easier to express. So instead of needing to expand your application downwards until you can find the lower parts of the language that actually act as a foundation to it, you can build up your language to make it easy and simple to express your application. And doing that will save you a bunch of time, because now you've got a much easier way to represent your application. The don't repeat yourself principle, dry principle. You can write an abstraction with a multi-stage operator and then never get writing that operation wrong. Rather than needing to remember to close a file every time you open it in the same scope, you can write a macro that will, with file, open the file and then defer closing it until it exits scope. And then you don't need to remember to close files that you open with that because it does it for you. You can write extensions that will make it easier for you to write whatever domain-specific platform you're doing without needing to put in the effort of writing an entire DSL, because it's designed to make that easy and fast. So, simplicity. It's also, multi-stage programming also makes your languages simpler. You've got a smaller core language. In Terra, you don't have namespaces and object systems as a separate thing of the compiler. Because of the way it's embedded in Lua code, you just get those, and you can manipulate them easily and effectively in whatever way you want, essentially for free. It makes the language simpler, easier to write, easier to compile, and that means that when you're maintaining, that the maintainers of the language can spend more effort on making the language faster and putting in thought to making the features as good as possible, since they have a smaller set of them that they need to maintain. It makes it versatile. Because you can easily abstract and write your own operations and operators in ways that you couldn't in non-multi-stage programming, you can make them more flexible and versatile than you would ordinarily get, which saves you time, lets you put in effort to optimize your code better, and it makes it easier to catch errors. And composability. In multi-stage programming, things become composable that weren't before. For instance, the act of unrolling a loop, once you write a multi-stage operator for it, is now something composable, is a composable abstraction that you can put anywhere you want. So, don't repeat yourself. I've mentioned this before, just reviewing the presentation at this point because we're about to run out of time. You get more possible abstractions. You can write types of abstractions you can't otherwise. You can write more performant abstractions, and because you don't need to deal with a ton of indirection. There are some things you can either do with multi-stage programming or with C#'s object system, but doing them with C#'s object system will